Okay. So let me just, any doubts about last time? So what we are going to talk about is humidity. So if you have seen in your 11th, 12th standard, something called as a phase diagram, right? We talked about it very briefly when Arya was asking about CO2. So if you think in terms of temperature and pressure, we show different regions in this phase diagram: the solid, liquid, and vapor region. The solid, liquid, and vapor regions are typically like this, right? So we have a solid region here, we have a liquid region here, and we have a vapor or a gas region here, right? So if you think in terms of water, this would be ice, this would be water, and this would be water vapor. When we say water, what we mean is water in the liquid form, right? And ice and water vapor. Oops, should not remove this line. So this is our vapor. What is this point called? Anybody knows?
Triple point.
Triple point.
Triple point. Triple, because at that point all the three phases coexist, mean they are in equilibrium with each other. So for water it is very close to 0 degrees centigrade, and pressure is very low, some 600 kPa or something, 100 Pascal or something like that. So don't worry about that. uh, Anybody knows what this point is called as? This point? Anybody knows what this point is called as?
No, sir.
Now
So critical
Critical
point.
point.
critical point, right? Right. What is the meaning of that critical point?
Sir, it is the temperature above which the gas cannot exist as a liquid given any amount of pressure.
Or vice versa, if you are talking about beyond this critical pressure and critical temperature, there is no way I can liquefy. If you are looking at this, if you are at this point, even if you reduce the temperature, there is no way I can liquefy. It does not liquefy. If I'm let's say here, there is no way I can increase pressure and liquefy. If you are anywhere below this critical temperature and pressure, that is the way uh, you can liquefy or you can vaporize some substance. So if you think about water, now what we are going to look at is more closely this equilibrium between the liquid water and the vapor water, right? That's what we are going to look at more in detail and do more calculations. So if you think about water, if I say temperature is 100 degrees centigrade, then this pressure would be 1 atmosphere, corresponding to this point on the blue line. What does that mean? That means water will coexist, water will be in equilibrium in the vapor state and liquid state at 1 atmosphere and 100 degrees centigrade. So when we take water, when we boil water, water boils at 100 degrees centigrade. That means liquid and vapor both are in equilibrium with each other, or both exist, both phases can exist at 100 degrees centigrade and 1 atmosphere pressure. If I increase pressure at 100 degrees centigrade, if I go to higher pressure, let's say 2 atmospheres, 5 atmospheres, 10 atmospheres, then water will exist only in the liquid state. Whereas if I keep the pressure as 1 atmosphere and increase temperature to maybe let's say 200 degrees centigrade, water will exist in the vapor state. Okay. Anywhere along this blue line, liquid and water are in coexistence. Now, and liquid and water can exist in equilibrium with each other. Okay, so we need to have a equation that describes this equilibrium between liquid and vapor state. Anybody knows what this equilibrium or the pressure corresponding to this particular temperature is called as?
Vapor pressure.
Right. So at 100 degrees centigrade, so at any temperature, the pressure corresponding to this blue line is called as vapor pressure. So at 100 degrees centigrade, vapor pressure would be 1 atmosphere. At 200 degrees centigrade, vapor pressure would be something else. We will talk about what it will be. At 50 degrees centigrade, vapor pressure will be something else. Okay. At 30 degrees centigrade, if I take water in a bottle, at 30 degrees centigrade, vapor pressure would be close to 30 millimeters of mercury. What does that mean? That means if I take liquid water at 30 degrees centigrade and I reduce the pressure, suppose I take it in a closed container and reduce the total pressure to 30 millimeters of mercury, then this water will start boiling because now liquid and vapor can exist with each other. Okay. Or alternatively, if you want, if I take liquid water and let's say I take it in a container, beaker, bottle, whatever you like, let's say total pressure is 1 atmosphere. I keep the bottle open to atmosphere. Now in this gap, in this space, we call this as head space. Head space is what is over a liquid in a container. What is this head space going to contain?
Air
Air
and
and
Air,
water vapors.
right? Air and water vapor.
water vapors.
Right. So air and water vapor both. Now, if you think about the equilibrium between liquid and water, if you look at it at a molecular level, what is happening at a molecular level? There are molecules of water. There are molecules of water vapor in the air. Air we are not showing. We are only looking at water and water vapor. So these molecules, now if you have thought about or if you have learnt in your physics, Boltzmann distribution of kinetic energy of molecules. Have you heard about that? Yes, no.
Yes, sir.
Okay.
Yes, sir.
Anyway, even if you have not heard, doesn't matter. These molecules of water in the liquid state will have a tendency to go into vapor state, and the molecules in the vapor phase will have a tendency to come into the liquid phase, right? So that is what decides the equilibrium. So there is an equilibrium between the vaporization and condensation. Now, only thing is, if the amount of water vapor in the air is very less, if the amount of water vapor in the air is very less, then the rate of condensation is smaller than rate of evaporation, and therefore no water actually condenses. Okay? But we can visualize a layer in the immediate vicinity of this liquid layer. So this layer in the immediate vicinity, we call this as interface. It is an interface between liquid water and the air above it. So layer in the immediate vicinity, which we call as interface. Let me write that. Called as interface, is at equilibrium between the water vapor, water vapor and liquid water. So this rest of the air that is there, this need not be at equilibrium, but the interface is always at equilibrium. Okay. Now this is a very important concept. We are going to employ, or we are going to use this concept everywhere in all subjects for the rest of our lives. Why? Because that interface layer is in the immediate vicinity of the liquid water, and therefore the rate of vaporization and rate of condensation in that layer have reached equal rates, and therefore that interface, that immediate layer, is always at equilibrium. And we are going to make this assumption, or we are going to let's not call this as assumption, we are going to use this principle in all the separation processes that you are going to come across in your second year and third year. Separation processes like distillation, extraction, right, humidification, dehumidification, all these concepts you will come across in your second year and third year. All of them we are going to make or take help of this principle, that the interface is always at equilibrium between the water vapor and the liquid water. So if I take this water at 30 degrees centigrade, okay, and let's say vapor pressure of water at 30 degrees centigrade is say 30 mmHg. Let's just make that assumption just now. Okay, and we will actually calculate what this vapor pressure is. Okay, but if I assume right now that vapor pressure of water at 30 degrees centigrade is 30 mmHg, that means at this interface, vapor pressure of water is 30 degrees cent is 30 mmHg. Okay, now if I take a sample of air near the interface, so suppose I take a sample here, if I take a sample of air near the interface, when I say near the interface, I should actually say at the interface, meaning layer immediately above the liquid layer, liquid water. Okay, so this layer maybe it is like maybe 2-3 mean free paths, or 5 mean free paths, or 10 mean free paths. That kind of layer that I'm saying. that distance. This layer is going to contain different things. This layer of air is going to contain nitrogen, oxygen, and water vapor. This nitrogen and oxygen mixture, we are going to assume that air is going to contain 79% by moles nitrogen, 21% by moles oxygen. So this we are going to call as dry air. Right? Now, if total pressure is 1 atmosphere, and let's say YH2O is the mole fraction of water vapor, then partial pressure of water vapor would be equal to YH2O multiplied by the total pressure. Okay, and because it is saturated meaning it is at equilibrium, because it is at equilibrium, the partial pressure of water vapor would be equal to vapor pressure at 30 degrees centigrade, because our liquid water is at 30 degrees centigrade. But if I take a sample of air here, from here, now this is going to contain dry air and it is going to contain water vapor. Total pressure is still 1 atmosphere. That beaker or that bottle is open to atmosphere. Now, if I say YH2O is the mole fraction of water vapor at this location, then partial pressure of water vapor at this location would be YH2O multiplied by total pressure. Right? But this air is not at equilibrium with this liquid water. This is not in equilibrium because we are not allowed time, or maybe because we are saying it is atmospheric air. So that atmospheric air is not in equilibrium with the water in your bottle, right? So then what can we say about partial pressure of water vapor in this air and vapor pressure of water at 30 degrees centigrade at the temperature of your water in the bottle? What can we say about these two?
They won't be equal.
They won't be equal. Which would be higher, which would be lower?
So the vapor pressure would be higher.
Right, vapor pressure is higher. So partial pressure is always less than or equal to vapor pressure. Right? So at the interface, they are in equilibrium. At the interface, they are in equilibrium. So this interface, we say it is always at equilibrium. And we say, or another word that we use is saturated. Interface is saturated. We'll talk about this as we go along. This ratio, one second, just let me complete. This ratio, partial pressure of water vapor, this ratio of partial pressure of water vapor divided by vapor pressure at the temperature of the liquid, in this particular case at 30 degrees centigrade. So this ratio is always less than or equal to 1. At the interface, it is equal to 1. Anywhere else, it is not equal to 1. And if we multiply this by 100, we will get percentage of equilibrium. In particular, we call this as percentage saturation, or more specifically, we call it as percentage relative saturation. And for air and water vapor, we use another special word. We call this as percent relative humidity. Okay, or percent RH. Let's do some calculations, and then all these things would be little bit more clear to you. Yeah. Somebody had a doubt? Please ask.
Sir, the partial pressure of water vapor is equals to Y of H2O into pressure total above interface also
Yes, it is everywhere.
everywhere equal.
Partial
Okay.
pressure is equal to mole fraction into total pressure. That is valid whether we are at equilibrium or not at equilibrium, isn't it?
Yes, sir. Yes.
Whether we are talking about air, whether we are talking about the room, whether we are talking about moon, whether we are talking about Jupiter, whether we are talking about Uranus, Neptune, Pluto, whichever is your favorite planet, sun, isn't it?
Yes, sir. Yes.
Right. Let's do some calculations, and then all these things could be little bit more clear to you. So we need a way of calculating the vapor pressure at any temperature, right? So we need to be able to calculate vapor pressure at any temperature. Does anybody know how we can calculate that? Anybody knows what this equation is called as? There is an equation that relates vapor pressure and temperature.
Clapeyron.
Ah, very nice. What is Clapeyron equation? Can you tell me the equation? Who was answering?
The log of P2 by P1 comes on one side. Remember that.
Log of P2 by P1. I'll give a chocolate if anybody knows this equation.
And then
Sir,
there is
Sir, it
log
was
of
on the paper
is equal
that
to
you sent
delta
us.
See,
03
with the
in bracket 1 by T1 minus 1 by T2
ln P2 by P1.
is equal to delta H divided by 2.303 1 by T2 minus 1 by T1.
Where is this 2.303 come from?
Sir, use
The log
R
of
instead of 2.303.
So R is 2.303.
No, he's wrong, but I
Uh-huh.
am suggesting improvement.
Okay, 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 okay. So that's the problem about 12 standard, that we are not taught properly the units. So we mug up all kinds of equations and all kinds of formulae without understanding that they are meant for only a certain specific set of units. Whereas now we are able to talk about any units, and we are able to convert anything from any unit to any other unit, right? So the equation is actually this. So it is actually vapor pressure. What about this?
Yes, sir.
And then if you integrate this between any pressure, vapor pressure 1 and vapor pressure 2, and temperature 1 and temperature 2, so you will get ln P2 by P1 as delta H by R, 1 by T1 minus 1 by T2. In general, we can write this expression, it is actually vapor pressure. We can write this expression as ln Vp as some constant A minus B by T. So this is like Y is equal to mx plus C. So this is your Y, this is your minus, this is your M, and this is your C, and X is 1 by T, right? So if you want to rewrite this as B divided by 1 by T. So 1 by T is your X, ln Vp is your Y, A is your intercept, and M is now your minus B, right? So this is your Clausius-Clapeyron equation. But the only problem is now we will talk about this Clausius-Clapeyron equation, more about Clausius-Clapeyron equation. We are going to talk more how this equilibrium. So in general, describing the equilibrium, equilibrium between two phases. In this case, what are the two phases that we have? Liquid water is one phase and water vapor is another phase. So this is a part of chemical engineering thermodynamics 1 and chemical engineering thermodynamics 2. This you will do in your semester 3 and semester 4, and there you will talk about more about this Clausius-Clapeyron equation. But we are going to talk about many such equilibria, and we are going to describe them mathematically in a unified manner. Here we are talking only about equilibrium between liquid water and water vapor, but we could talk about equilibrium between the solid water, meaning ice, and liquid water, or we could talk about equilibrium between the solid water, means ice, and water vapor, meaning sublimation or desublimation of water. We could talk about any of these equilibria. We could talk about an equilibrium between gas and a liquid. We could talk about equilibrium between two vapors and two liquids. All those things we will do mathematically in a course called as Chem Eng Thermodynamics 1 and Chem Eng Thermodynamics 2. They are coming in semester 3 and semester 4. So then you will know better about how to describe mathematically this equilibrium in a unified format. Right now, we are just going to use this kind of equation, right? And we are going to make some small modification to this equation, because this equation, the Clausius-Clapeyron equation, is valid over a narrow temperature region. Why? Because it is differential. It is dt. dt we have made it into a difference equation, right? So dt we have made it into 1 by t1 minus 1 by t2, right? And that assumes that this delta H is constant. But in reality, the delta H is not constant. Therefore, this is valid only over a narrow region of temperature, right? So we have, if you are with me, we have gone like this: d ln Vp is equal to delta H by RT square dt. And we have integrated this between T1 and T2 and Vp1 and Vp2. And that integration has been possible only because delta H we have taken outside the integral. We have assumed delta H is constant, right? But that's not quite correct. And therefore, the Clausius-Clapeyron equation is valid as delta H as a constant only over a narrow range. So this equation is valid only over a narrow range of temperatures. But we need to be able to calculate vapor pressure anywhere between the triple point and the critical point. All this blue line we should be able to calculate the vapor pressure of water. Just so, for example, just for water, this triple point is very close to 0 degrees centigrade, right? And this critical point is is beyond 400 degrees centigrade. 420. Don't worry about the actual number, right? But it is beyond 400 degrees centigrade. Pressure is practically at triple point. Pressure is very small, maybe few hundred of Pascal, whereas pressure at the critical point is more than 200 atmospheres. So it is not a narrow range. It is not a narrow range for water from triple point to critical point is not a narrow range. And therefore this is not valid over the whole range. It is valid only over a small range of temperatures. So people took this equation, people actually measured this temperature and pressure. At this temperature, what is the vapor pressure? 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 People actually made measurements and fitted an equation which looks like this. ln Vp is equal to A minus B divided by T, and some constant was added. So A, B and C, these are constants. And this equation now is valid over a wider range of temperatures. We call this equation as Antoine equation. Okay. So A, B, C are constants for a particular substance. So for water, I will have a certain value of A, I will have a certain value of B, I will have a certain value of C. If I take toluene, I will have a different value of A, B, C. If I take benzene, I will have a different value of A, B, C. If I take acetic acid, I will have a different value of A, B, C. So for every substance, there are three different constants which relate the vapor pressure to the temperature. So this sometimes this vapor pressure either is given in terms of in the natural log form, or sometimes it is given in the log to the base 10. Again, so you will have a new constant, some A1 minus B divided by T plus another constant C1. Constants will obviously be different. Sometimes this temperature is given in units of Kelvin. Sometimes it is given in units of degrees centigrade. So temperature can be in Kelvin, it can be degrees centigrade, it can be degrees Fahrenheit, whatever you like. And vapor pressure, it can be in any pressure unit. It can be in terms of mmHg, it can be bar, it can be kilopascal, it can be atmospheres, it can be psi. Whatever set of units of pressure you want, your equation can be written in that particular set of units. Okay, so we'll start doing some calculations. If there are any doubts up to this point, we can quickly discuss. Otherwise, we'll start doing calculations, and many of these things would become automatically very clear by the time we start doing calculations. Shall we go to calculations?
Sir, it is
Yeah.
not compulsory that temperature must be in Kelvin like this. In
Yeah,
the
so that's what I'm saying. Temperature can be in any set of units: Kelvin, degrees centigrade, degrees Fahrenheit. This can be in pressure, can be mmHg, bar, kilopascal, pascal, atmosphere, psi, any unit of pressure, any unit of temperature.
So we can
Correspondingly, the
directly.
constants will be different.
Okay, so constants will be given. Okay, sir. Thank you.
Right. Can we go to the calculations? Yes, no?
Yes, sir.
Yes, sir.
All right. So let's do basic calculations. I'm going to tell you vapor pressure of water. I'm going to give you an Antoine equation. That's like this. ln Vp is equal to 18.3036 minus 3816.44 T minus 46.13. Okay. And here vapor pressure is in the form of mmHg, is in the units of mmHg, and temperature is in units of Kelvin. Okay. So if you just look at, suppose temperature is 100 degrees centigrade, which means 373.15 Kelvin. Can you tell me what is the vapor pressure? Calculate. For attending this lecture, you must have a calculator with you. And you should be doing calculations all the time. Somebody calculate.
Sir, I am getting 760.
So that is 1 atmosphere. Anybody else? Only one person is attending
Yes,
the
sir,
lecture.
it's approximately 7.
Yeah, because this is a correlation. So that experiment correlation has some error associated with it. Right? Only 2 people are attending the lecture.
So yes, it's 760.
3.
So it's 760, sir.
Yes, sir, 760.
Sorry.
Yes, sir, 7.
I'm surprised. Many more are attending lecture.
760.
760.
Okay. Let's calculate. Suppose temperature is 30 degrees centigrade. Calculate vapor pressure. Suppose temperature is 50 degrees centigrade. Calculate vapor pressure. Suppose temperature is 70 degrees centigrade. Calculate vapor pressure. And suppose vapor pressure is let's say 125 mmHg. Calculate temperature in degrees centigrade. Vapor pressure also I want in different units. Let's do this very quickly.
Sir, at 30 degrees, it is 31.65.
Okay.
Sir, it is 31.39.
Okay. Okay. 50 degrees centigrade.
Sir, 31.65.
Sir, at 50, 91.8.
What? 91.8 what?
of Hg.
But I want answer in kilopascal. So convert. Convert to
So
kilopascal.
it's 12.2 kilopascal.
12.2 kilopascal. Okay.
Sir, 12.32 kilopascals.
Okay.
So 12.3.
Yeah. Okay.
So 12.3.
Yeah. Let's go to 70 degrees centigrade.
Temperature 56 degrees Celsius.
56 degrees Celsius.
4.5 psi. 4.52.
Okay. Can we go forward? Don't worry. Even if you have not finished, you can do later. I'm going to share recording, so no problem. Can we go forward?
Yes, sir.
Yes.
Yes, sir.
Okay. Now imagine it is raining outside. Right? Or, okay. Now don't imagine that there is rain outside. Okay. So imagine that you are in some country where it is not raining. Okay. So or some part of India where it is not raining. So this ambient air now. Okay. So let's say this is your air. Right. Let's assume that total pressure is 1 atmosphere, which means 760 mmHg. Okay. Now this air is going to contain nitrogen, oxygen, and water vapor. Okay. So the nitrogen and oxygen part, we call it as dry air. And in this dry air contains 79 mole percent nitrogen and 21 mole percent oxygen, or volume percent if you like. They are the same. Now suppose temperature is 40 degrees centigrade. Right? Suppose temperature is 40 degrees centigrade. What is the water? No, let's not take 40 degrees centigrade. Let's take, let's say 50 degrees centigrade, because we already have an answer for 50 degrees centigrade. So suppose temperature is 50 degrees centigrade. Now, what is the vapor pressure at 50 degrees centigrade? This is 91 mmHg. Right? But if I take a sample of the air, and calculate mole fraction of water vapor, let me just say mole fraction of water vapor multiplied by the total pressure, that is going to tell me 760 multiplied by mole fraction of water vapor. That is going to tell me so many millimeters of mercury. This is our partial pressure of water vapor. Right? That means in this air, partial pressure of water vapor can be anything up to 91 millimeters of mercury. It cannot be more than 91 millimeters of mercury. Why? Because if it became more than 91 millimeters of mercury, then liquid water will start condensing out, isn't it? Because that's the equilibrium between liquid and vapor. So if it exceeds 91 millimeter of mercury, then it will start condensing, and at the most air can have partial pressure of water vapor equal to 91 millimeters of mercury in this at this particular temperature. So this ratio of partial pressure divided by vapor pressure into 100 we call as percent relative humidity. Okay, so now suppose you are somewhere in Rajasthan, let's say temperature is 50 degrees centigrade, very hot summer day, and I tell you, you look at the newspaper, you find out percent relative humidity. So let's say percent humidity is 45%. What would that mean? That means partial pressure of water vapor would be, or divided by vapor pressure of water into 100, this is 45, right? So partial pressure of water vapor would be 0.45 times vapor pressure at 50 degrees centigrade. This is 91 mmHg. So somebody calculate 0.45 multiplied by 91.
40.95.
40.9.
40.95 mmHg. Partial pressure of water vapor. So that is the partial pressure of water vapor in the air is 40.95 mmHg. What is the mole fraction of water vapor in the air? Mole fraction. How do you get the mole fraction?
So partial pressure upon total pressure.
Right. So it is
0.05.
40.95 divided by 760. Somebody calculate.
0.053.
0.05388.
0.054, let's say. Okay. And the mole fraction of dry air part of it, dry air, is 1 minus mole fraction of water vapor. We are assuming that air is going to contain only nitrogen, oxygen, the dry air part of it, and the water vapor. So dry air can be anything: nitrogen, oxygen, helium, carbon dioxide, argon, methane, whatever else you want to consider. All of that is the dry air part of it, and 1 minus water vapor part of it. So that is 1 minus 0.054. That means this is 0.9, whatever, 0.946 something. Okay. Is that okay? So far, so good. Can we go forward? Can you tell me? Can you tell me? So far, so good. Can you go ahead? Can we go ahead?
Yes, sir.
Yeah. So can you tell me what is the moles of water vapor divided by moles of dry air? How will we calculate that? How would we calculate this?
Basis, sir, 100.
Yeah, if I
So
take basis
0.
as, yes, if I take basis as 100 moles of this air, out of this 100 moles, how many moles of water vapor would there be? Who was answering 100 moles? Who wanted basis of 100 moles? Somebody wanted a basis of
Take, sir, 0.5, sir. 0.54. No, sir, 0.54. 0.54 water.
You are answering 0.54, you are answering 0.054. Take a deep breath.
0.54.
Take a deep breath. Have a glass of water. If I take basis as 100 gram
5.4.
moles,
5.4, sir.
5.4.
oh, chill, relax. You are not. There is no need to hurry, right? We don't have to. We don't have to. We don't have to answer in a hurry, right? Take your time.
Sir, we can take the ratio of the two.
Yeah.
Yes, sir.
Yeah. Okay. Let me just explain. Whoever wanted this 100 gram moles as basis, okay, fine. We take 100 gram moles of basis. Then moles of water vapor would be 100 multiplied by 0.054, because mole fraction is 0.054. Moles of dry air would be 100 multiplied by 0.946. Right. So this 100, whether I take basis as 100, whether I take basis as 1, they just it just cancels out. Do you agree? Whoever was telling me 100 basis, do you
Yes, sir.
agree? Or 0.054 divided by 0.946? Atharva, you were telling, who was telling?
Yes, sir.
Okay. Point. So this is 0.057. All right. Can somebody tell me how many kgs of water vapor are there in the air per kg of dry air? How will I calculate that?
So now we have to take a basis and then calculate.
No, you do whatever you like. Can somebody tell me how to calculate? Can somebody calculate and tell me whether you want basis, you don't want basis? When you do this, you have automatically taken basis as 1 mole of the mixture, air mixture. Whether you like it or not, whether you understood or not, whether you define explicitly basis or you don't define explicitly basis. But a good idea to take basis as 100 moles of the mixture. That way we are very clear. It is 100 multiplied by mole fraction. It is 100 multiplied by mole fraction of dry air. The 100 just cancels out. Can you tell me how many kgs of water vapor will there be per kg of dry air?
Sir, 4.9 into 10 power minus 4.
One chocolate who tells me the right answer.
Sir, I'm getting the answer which is vaguely different from Arya's.
It doesn't
It's
matter. You tell me your
0.
answer.
0.0355.
Yes, sir. Even I'm getting zero point zero
Yes,
three
yes,
five.
sir. I am also getting that.
0.035.
Many people are getting this answer.
0.035.
0.03.
How do you calculate? How did you get this 0.035?
Sir, I multiplied the 0.057 into the molar mass of water and upon the average molar mass of dry air.
Right. So if you take this, continue the same basis, 100 moles or 100 kilomoles in this particular case, then I would have 0.054 kilomoles of water vapor, and I would have 0.946 kilomoles of dry air. So if I want to find out kilograms of water vapor, I would have to multiply this by the molecular weight of water, and I would have to multiply this by molecular weight of dry air. So molecular weight of water is straightforward, 18, right? Molecular weight of dry air, so that is 79 mole percent nitrogen, 21 mole percent oxygen. So if I take 100 kilomoles of dry air, I'm taking a different basis to calculate this molecular weight. If I take 100 kilomoles of the dry air, I have 79 kilomoles of nitrogen. I have 21 kilomoles of oxygen. 79 kilomoles of nitrogen would be 79 multiplied by 28 kgs of nitrogen. 21 kilomoles of oxygen will be 21 multiplied by 32 kilograms of oxygen. If I add them up, this will be the total kgs of dry air. What is this total coming from? 2884. It is coming from 100 kilomoles of dry air. So it is like average molecular weight of dry air is weight 2884 divided by the total moles that are there. So this would be 28.84, right? So kgs of water vapor per kg of dry air, I need to multiply by molecular weight of dry air. That would be 28.84. So this number would be around 0.035 something. Are you able to have you found out where you went wrong?
Yes, sir. It was a calculation mistake.
Okay, doesn't matter. Okay, can we go forward? Can we go forward? Can we go to the next problem? Do you want a small break of 5 minutes? Just so that you think about all these things, not for you to play some game and check your WhatsApp. Do you want a break for 5 minutes or shall we continue?
Break, sir.
Break for
Break would
5
be fine,
minutes.
sir.
Yeah, so we'll just break for 5 minutes exactly. Okay, reassemble in 5 minutes. Don't go away, don't reassemble, be here only.
Sir, can you scroll up a little bit?
Okay, shall we begin?
So, one doubt.
Yeah.
Why do we have the Why do we have the interface at equilibrium? Like, why do we assume that?
Because interface is an immediate vicinity, right? It is like one molecular thick. Not one molecule thick, but it is like, let's say, 100 molecules thick. So that equilibrium between the water vapor molecule. So if you zoom into the interface, right? If you zoom into the interface, so this is your interface. I don't think I can zoom in any further. It is maximum zooming in possible. So that liquid water molecules escaping and vapor water molecules condensing, that equilibrium reaches very, very quickly because the interface region is very, very small in size. It has stopped working. Uh, is that okay? So that's why we say interface is always saturated.
Yes, sir. Okay, understood.
It's like one layer, not one physically, but I mean, imagine five molecule thickness. So then the equilibrium between water vapor molecules escaping and the liquid water molecules condensing. So liquid water molecules escaping and vapor water molecules condensing. Those processes occur at a certain rate, and if the amount to be equilibrated is small, that equilibrium will be established practically instantaneously. Okay, shall we go to the next problem? We will come to interface again and again throughout our lives.
Yes, sir.
Can we go to the next problem?
Yes, sir.
Okay. So here's the next problem, this next concept, which we are just calculating by way of a problem. So imagine that we have, okay, in another place now, let's say you are in some other part of our country. So let's say air, ambient air.
Sir, we cannot see the screen.
Oh, sorry. Yeah. Because it created a problem. Yes. Are you able to see now?
Yes, sir.
Okay. Okay. So let's say ambient air, you are in another part of the country. Let's say total pressure is 745 mmHg. Temperature is 32 degrees centigrade. Percent RH is, let's say, 75. Okay. Calculate kgs of water vapor per kg of dry air. Calculate this number. This number is called as humidity. It is denoted by letter H. So calculate for this particular case. You can look at your notes, how you have done the previous problem, and then you can calculate for this particular problem. Any answer? Only 3-4 people give me answers. I want answer from some other people who have not answered so far. Abhay, can you tell me the answer?
Sir, I'm doing.
Okay. Bhakti, can you tell me the answer?
Sir, I'm doing it.
Once you finish, can you tell me the answer?
Okay, sir, I'll try.
Sir, I am getting 0.0231.
We'll wait for Bhakti to tell the answer.
Sir, I get 0.032.
Okay, we'll wait for Bhakti. Even if you got some intermediate values, you can tell us. Or how did you calculate? You can tell us.
Sir, actually, I'm not getting it.
Okay. You look at the previous problem.
Okay, sir, I'll look at it.
When we were doing the previous problem, were you also doing simultaneously or not doing simultaneously?
I was looking at it. Like you were explaining it, I was just
Okay.
looking at it. I didn't solve it simultaneously.
Okay, now you solve
Yes,
this
sir.
one. Look at that
Sir,
and
I'm getting at 0.0229.
okay.
Sir, I am getting 0.023.
0.022.
Okay.
So 0.023.
Sir,
Okay.
0.022623.
Sir, 0.0224.
So 0.0226, that is 0.023.
We'll wait for Bhakti.
Yes, sir, 0.0226.
Should I explain or you want to try, Bhakti?
Sir, can you please explain it?
Okay. So now we want kgs of water vapor per kg of dry air, right? So we want to know essentially how many kgs of water vapor are there in this air, right? So we would like to know what is the mole fraction of water vapor in this air, or we would like to know what is the partial pressure of water vapor in this air, right? So to calculate partial pressure, but we know what is percent relative humidity. So if I calculate the vapor pressure, at 32 degrees centigrade, then I will be able to calculate partial pressure. So first thing is to calculate vapor pressure at 32 degrees centigrade. How we are going to calculate that? We are going to use Antoine equation. Where is that Antoine equation gone? Yeah, here is that Antoine equation. So if I take 32 degrees centigrade, Bhakti, now you calculate vapor pressure based on this equation.
Yes, sir.
And then we'll wait for you to calculate.
So I am getting it as 35.48.
Correct. So vapor pressure is 35.48. Let's just say 35.5 mmHg. We should always be rounding off. Okay. So now tell me, what is the partial pressure? What is the definition of relative humidity? Relative humidity is partial pressure divided by vapor pressure multiplied by 100. So partial pressure would be 0.75 times 35.5. Right. Okay or not?
Yes, sir.
26.6 mmHg. So now tell me, what is the moles of water vapor per mole of dry air? So this is the partial pressure of water vapor. What must be the partial pressure of dry air? Total pressure 745 minus partial pressure of water vapor, isn't it?
Yes, sir.
So that must be 718.4 mmHg. So now moles of water vapor per mole of dry air would be 26.6 divided by total pressure 745 minus 26.6, that is 26.6 divided by 718.4. So now tell me, kgs of water vapor per kg of dry air, that would be this number multiplied by molecular weight of air divided by molecular weight of dry air. Right? Is that okay?
Yes, sir.
So this would be 0.023 kgs of water vapor per kg of dry air. Now, are you comfortable? Is that okay? Can we go ahead?
Yes, sir. Thank you, sir.
Yeah, no problem. Okay. So now this air is going to contain 23.023 kilograms of water vapor per kg of dry air, or 23 grams of water vapor per kg of dry air. Now you remember your sulfuric acid problem, flow sheet problem? Do you remember that problem? We had
Yes,
this
sir.
air dryer. We had taken this 20 grams of water vapor per kg of dry air. Do you remember that?
Yes, sir.
So that is coming from these kinds of calculations. Okay, can we go forward?
Yes, sir.
Sure.
Okay, now suppose I take this air. Suppose I take this air. It has a total pressure of 745 mmHg. Ambient air, I mean, we are not actually physically taking it, or if you want, we can physically take it, but it is ambient air. Total pressure is constant, 745 mmHg. Temperature is 32 degrees centigrade. Percent RH is 75, which means it has 0.023 kilograms of water vapor per kg of dry air, or if you like, it has a partial pressure of 26.6 mmHg. Dry air has a partial pressure of 718.4 mmHg. Now, suppose I keep the pressure constant, atmospheric pressure, okay, and reduce the temperature. Is that okay? So imagine I take a sample of this air connected by a frictionless, weightless piston. So this is the air, and total pressure is 745. So total pressure is going to remain the same because it is open to atmosphere, right? This piston, on this piston, atmospheric air is acting. Now I start cooling this air. I put this in a water bath, ice. I keep on putting ice, and I cool this air mixture, right? Is everybody able to visualize? So pressure remains the same. As I cool, the volume will of course reduce, but I'm not worried about the volume just now. I'm worried about something else. Okay, can we go ahead? Is everybody able to visualize? Yes or no?
So can you please repeat it once?
So I take this air, I take a sample of this air, put it in a container, and I start cooling this container. And because it is container is with a piston, let's say, it is movable so that the pressure remains constant. Obviously, as I cool, the volume will reduce, right? Ideal gas law. But I'm not worried about volume just now. I'm worried about something else. Are you able to visualize the situation?
Yes, sir.
Yes, sir.
Okay. So now I reduce the temperature. Suppose I reduce the temperature to 31 degrees centigrade. Suppose I reduce it to 30 degrees centigrade. Suppose I reduce it to 29 degrees centigrade. Can I keep on reducing? Will something happen at some particular temperature?
So the water vapor will liquefy.
Yes, so some of it will liquefy. Let's look at that. So imagine that temperature is 31 degrees centigrade. Can somebody tell me vapor pressure corresponding to 31 degrees centigrade? Can somebody tell me vapor pressure corresponding to 30 degrees centigrade? Can somebody tell me vapor pressure corresponding to 29 degrees centigrade? Somebody tell me vapor pressure corresponding to 28 degrees centigrade? Somebody tell me vapor pressure corresponding to 27 degrees centigrade? Somebody tell me vapor pressure corresponding to 26 degrees centigrade? Somebody tell me vapor pressure corresponding to 25 degrees centigrade? Somebody calculate fast. Everybody doesn't have to calculate everything.
For 31, it is 33.52.
33.5.
So for 28 degrees Celsius, it is 28.163.
So for 30 degrees, it is 33.599.
30 degrees it is?
1 minute, sir.
31.65.
31.65.
Okay.
Yes, sir.
So for
Sir,
25, it
for
is 23.6.
23.6.
sir,
Okay.
for 27, it is 26.56.
Sir, for 29, 29.9.
Only 26 degrees centigrade is remaining now. Oh, so sorry.
25.02.
25.02, 26.5, let's say. Now, can you tell me, if I keep on reducing the temperature to 31, partial pressure is 26.6, but vapor pressure is 33.5. Is that okay? Partial pressure is less than vapor pressure, so no problem. Cool it further, vapor pressure reduces. 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 What does that tell you? If I calculate percent RH at this temperature, percent RH will be less than 100. At this, it 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 will try to become more than 100. Isn't it? That means air will become more than saturated. So then liquid water will form. Some of the water vapor will be converted into liquid water. Correct? Now cool it further. Cool it further. Some more liquid water will form. Some more liquid water will form. Right? Do you agree with that? But beyond this particular temperature, as liquid water will start condensing out, what will happen to partial pressure of water vapor at, let's say, 25 degrees centigrade? Maximum that it can hold is going to be equal to vapor pressure of water vapor at 25 degrees centigrade. At 26 degrees centigrade, partial pressure could be, maximum possible value is vapor pressure at 26 degrees centigrade. So beyond this particular temperature at which first drop of water starts condensing, water will
It
start,
becomes constant.
water
The
will,
value.
liquid water will start forming, right? More and more liquid water will form, more and more of the water vapor will condense into the liquid form, but the air now will become 100% saturated, or air will have 100% RH beyond this temperature, beyond the temperature at which first drop of water appears. So that first drop of water that appears, we call it as dew point of water, or dew point of air, not water, dew point of air. Because air, if it is cooled up to that point, first drop will appear, first drop of water will appear. And then once that dew point appears, partial pressure would become equal to vapor pressure. And anything below that, partial pressure will always be equal to vapor pressure. That's the maximum amount of water vapor that can be accommodated in the air. Whatever else is over and above that, it will start condensing. Let's do a problem.
So can you repeat it again?
No, let's do a problem. I mean, yes, I can repeat, but that's not important. Once we do the problem, there'll be no need to repeat, because you will understand everything yourself.
Okay.
So now, if I want to find out,
so we can say that the solubility of water vapor in the air decreases. So
okay, let's not call it as solubility, because the word solubility we use generally for solids in liquid or for gases in liquid. We don't use that for this, but okay, let's not use any word, it doesn't matter. We let's find out dew point of this air. Right? So what is going to happen at dew point? Now the vapor pressure is going to become equal to the partial pressure, which means now vapor pressure is going to become 26.6 mmHg. So now if I use Antoine equation, ln Vp Antoine equation. This is the Antoine equation, right? You write it down somewhere so that you can use it again and again, so that I don't have to write it again and again. So now vapor pressure will become 26.6. So ln Vp. I'm just writing it for the first time. Now, once you write it down in your notebook, then I don't have to again write it. Vapor pressure is in mmHg, temperature is in Kelvin. So now for the dew point, that means vapor pressure has to become equal to partial pressure, or partial pressure will automatically become vapor pressure, because we are cooling, vapor pressure is reducing. Okay. And when these become equal, at that point, first drop of liquid water will appear, first drop of water will condense out. And then now we can use this Antoine equation. This will become ln 26.6 would be equal to 18.3036 minus 3816.44 divided by T minus 46.13. And if I solve this equation, somebody solve and calculate the temperature.
Sir, won't it be 27 only? Because we calculated that
Yeah,
one.
27 degrees centigrade. Okay, temperature you will get in Kelvin, okay, but then you convert to centigrade. So that means the dew point of this air is 27 degrees centigrade. Now let's go further. Okay, let's go further. Okay, suppose I take this air. Okay, so I have this air. Total pressure is 745 mmHg. Temperature is 32 degrees centigrade. Percent RH is 75%. Right? Same example. That means in this air, partial pressure is 26.6 mmHg. Okay. So if I cool it to 27 degrees centigrade, first drop of water will appear. If I cool it to 25, more water will form. If I cool it to 23, even more water will form. If I cool it to 21, even more liquid water will form. If I call it to 20, even more liquid water will form. Okay. Now here is the problem. Okay. I want you to calculate temperature to which this air should be cooled to condense out 80% of water. Okay, this is the problem. I want to condense 80% of the water in the form of liquid water. Right?
Sir, water vapor. No?
Whatever water vapor is there, okay, I want to condense out 80% of that and make it into liquid water. I want you to tell me at what temperature we should cool this air. Should I cool it to 5 degrees centigrade? Should I cool it to 25 degrees centigrade? Should I cool it to 15 degrees centigrade? Should I cool it to 17 degrees centigrade? What is that temperature to which I should cool so that 80% of the water vapor becomes liquid water? Okay, is the problem statement clear? So whoever had doubt, once you solve this problem, automatically your doubt will be answered. I know what your doubt would be.
Sir, 2 degrees, 2.62 degrees Celsius.
Okay. 2.6. That is one answer. We will wait for some other people also to calculate. Now this time we will wait for, let's see, whom shall we wait for? We will wait for Prajyot. Prajyot Patil. Prajyot, have you understood the problem?
Yes, sir.
You are doing?
Yes, sir.
Okay. If you are stuck somewhere, just ask.
Okay, sir.
Sir, I got 2.44 degrees Celsius.
Okay.
Sir, even I got 2.4.
Okay.
Yes, sir. 2.44.
Yes, sir. Even I would change my answer to 2.4.
Okay. We are waiting for Prajyot. Prajyot, any answer?
Sir, just 2 minutes, sir.
Okay, okay.
Sir, I am getting 1.12.
Okay.
Hello, sir.
Yeah,
Sir, I am getting 2.15. Sorry, 2.51.
2.5. Okay, 2.4, 2.5. They are all same. Okay, Prajot, can you tell us how you done the problem?
Sir, I assume basis has 100 moles of dry air.
Wait. Let me write. Basis as 100 moles of dry air.
Therefore, moles of H2O will be 3.7.
We should say moles of water vapor, right?
Yes, sir.
Would be
3.7.
how did you get 3.7? How did you get 3.7?
Sir, from above question. The last question we have done.
Yeah. Where was that? It was 0.054, right? Oh, so that was a different question. Yeah. So how did you calculate this? This must be 26.6 divided by 745, isn't it?
Yes.
So 26.6 divided by 745. This would be 0.035 into 100. So that means 3.57 gram moles of water vapor, and 100 minus 3.57. 100 minus 3. How much is it? 100 minus 3.57. Prajot, I'm waiting for you.
Yes, sir. Yes. 96.43.
96.43 gram moles of dry air. Okay, now tell us what you did.
No, sir. Sir, I assumed 100 moles of dry air.
Oh, sorry. So you assumed 100 moles of dry air.
Yes,
Okay,
sir.
then how did you get moles of water vapor?
Sir, I know mole fraction of H2O in water vapor. Sorry, in dry air.
Mole fraction of water vapor in dry air. How did you know
Means
that?
in air, it's 0.036 from last question.
0.0357 in air.
In air, yes, sir.
In air. Okay, now?
And I assumed 100 moles of dry air. So I
Okay.
will get moles of H2O.
How? Let's not, Prajot, let's not call it as H2O, because
Water
H2O
vapor,
can be
sorry,
in the
sir.
liquid state or in the vapor state. So let us call it as water vapor or water liquid. So moles of what now? Moles of water
Moles
vapor.
of water vapor in air.
Okay. How did you calculate that?
Sir, mole fraction is moles divided by total moles.
So 0.0357 multiplied by 100. Is that what you did? What is your
Sir,
basis? Your basis is dry air, 100 moles
yes,
of
sir.
dry air.
Dry air.
Whereas this is 0.0357 is containing dry air as well as water vapor. It is mole fraction in the air, right?
Yes, sir.
So then this is wrong. Now you tell me. Prajot, tell me how you calculated.
Yes, sir. Yes, sir.
You have to
Sir,
just speak up. I'm writing for you.
0.036 is equals to moles of H2O,
Okay,
moles of water vapor divided by moles of water vapor plus moles of dry air.
Very nice. So you are saying mole fraction of water vapor in the air is 0.036. So moles of water vapor divided by moles of water vapor plus moles of dry air is equal to 0.036. So moles of water vapor divided by moles of water vapor plus 100 is equal to 0.036.
From that we get moles of water vapor as 3.7.
Moles of water vapor is equal to
3.7.
3.7.
Yes, sir.
Okay, 3.7 gram moles. Okay, now what?
Now water is cooled to 80% of water vapor is condensed.
Correct.
Therefore, air has only 20% of water vapor.
So shall we say moles of water vapor remaining in the air?
Yes, sir. 20% of 3.7
is 20% of 3.7. So 0.2 multiplied by 3.7, how much is that?
0.74.
All right, 0.74 gram moles. Okay, now
Now I calculated mole fraction of H2O.
so mole fraction of H2. What H2O? H2O what?
Sorry, water vapor, sir.
Ah,
In the air.
water vapor in the air. How did you calculate that?
Sir, wait.
Sorry, you have only calculated. So you should be able to tell. Again, the same formula.
Yes, sir.
0.74 divided by 0.74 plus 100. Dry air
Ha,
part
sir.
is not changing.
Yes, sir.
How much is this number? 0.74 divided by 0.74 plus 100.
0.0072.
0.0072. Okay. I'm assuming your calculations are correct. I'm not checking your calculations.
Okay, sir.
Okay. Mole fraction of water vapor is 0.0072. Now
Then partial pressure, sir, of water vapor.
partial pressure of water vapor would be 0.0072 multiplied by total pressure. Total pressure is 745.
745.
Okay. How much is this number?
5.35 mm of Hg.
5.35 mmHg. Now,
Then that's a formula.
so now one important statement is that now the air that has been cooled, now liquid water has condensed out. So I have liquid water that has formed. The air that is there is now 100% saturated. It has 100% relative humidity because now water is condensed from that air. Therefore, the remaining air now has 100% relative humidity. So now it must be at a temperature such that the vapor pressure is 5.35 mmHg. This statement you have made in your mind, isn't it, Prajot?
Yes, sir.
So it is good idea to write that statement or at least make that statement. So now we have to just use the Antoine equation. So ln 5.35 is equal to 18.3036 minus 3816.44 divided by T minus 46.13. Temperature you will get in Kelvin. Solve this. Convert to temperature in degrees centigrade. And what was your answer, Prajot? 2.5.
2.51.
Forget that one. 2.5 degrees centigrade. Okay. Anybody has any doubts? But good point about Prajot's solution is that he defined basis very properly and did calculations based on that basis. Somebody else may take any other basis, but that's okay. Okay. Any
Sir,
other? Yes.
sir, doubt that if water is condensed, then relative humidity becomes 100%
Of the remaining air.
of the remaining always.
Because water has condensed, na?
Yes, sir.
It is water, whatever water vapor was there, it has now become liquid water. How much of liquid water will become? Only that much liquid water will become that the air can hold maximum possible amount of water. What is the maximum possible amount of water that air can hold? Would be corresponding to vapor pressure at that particular temperature. Isn't it?
Yes, sir.
Okay.
Okay, sir.
Okay. Any other difficulty? Can we go to the
Sir,
next problem?
sir, in the last question, we got partial pressure of water vapor as 26.6.
Huh.
So can we take that since 80% has been condensed, so 20% of 26.6 would be remaining.
80% of 26.6 is remaining. How is
It's
that?
condensed. So
80% of
20%.
26 point. No, we are not going to do calculations based on pressures. We are going to do calculations based on mole fractions.
Yeah, so the pressure would correspond to mole fraction. Right?
But it is generally not a good idea. The reason I am saying it is generally not a good idea is because something may happen in some other problems. There may be something happening to the remaining air also. So in general, yes, you can, but let us not do shortcuts of doing 80% of or 20% of 26.6 and all that.
Sir, uh, uh, am I audible, sir?
Yeah, you're audible.
Yes, sir. So for the 26.6 partial pressure, sir, the corresponding mole fraction, if we take 20% of that remains in air, accordingly, can we do it, sir? Like, that
Yeah,
makes sense.
you do any way you like. According to Prajot, based on this as a basis,
yes, sir.
He has done these calculations. Okay.
Yes, sir. But
Now
in this method,
I am not advocating any method. All I am saying is you take a basis which is you think is convenient to you, and accordingly do calculations with respect to thinking what is remaining, what is not remaining. So Prajot 100 gram moles of dry air as a basis, therefore this dry air became 100, this dry air became 100, therefore this became 100. It was very convenient for him because it did
yes, sir.
not change.
Understood, sir.
Is that okay? I'm
Yes,
not
sir.
advocating any method. I'm not advocating Prajot's method. I'm not advocating your method. I'm
Understood,
not
sir.
advocating any method.
Yes, sir.
All
But
I'm
in
saying is whatever is your method, do systematically.
okay, sir. Sir, is there any margin, like, is there any possibility of an error in our method, sir? Because for this one, it makes
So
sense,
I have
sir.
no
So
idea
this
what
can
your
be
method
extended.
is. I have no idea what your method is. So next problem, what we will do is we will ask you to tell us the solution, and then we will see your method, whether your method is right or wrong. Is that okay, Anirudh?
Okay, sir. Yes,
I don't want to comment because I have not seen your solution.
Understood, sir. Yes.
Had it been a class, I would have seen your solution. And therefore, I could have said, yes, your method is right, or no, your method is not wrong because of so and so reason.
Yes, sir.
So now, next problem, you tell us the solution, and we will see whether your method is right or wrong. Is that okay?
Yes, sir. Yes.
Okay. Now, same problem, same air. Okay. Next problem, air, 745 mm Hg total pressure. Temperature 32 degrees centigrade, percent RH. How much did we have? 75. 75. Now, what I will do is I will take this air. Now, I will put extra pressure on this piston. I will increase the total pressure. I will put weights on this piston, increase the total pressure. Under isothermal conditions. So I will maintain the temperature at 32 degrees centigrade, but we will increase the total pressure. Okay. So now if you increase the total pressure, now air that was there, that had some mole fraction, multiplied by total pressure, that was equal to partial pressure. Now total pressure is increased. This partial pressure will keep on increasing. If I double the total pressure, partial pressure will double. If I make the total pressure 10 times, partial pressure will become 10 times. At some value of partial pressure, at some value of partial pressure, at some value of total pressure, partial pressure will become more than vapor pressure at 32 degrees centigrade. And again, liquid water will start condensing out. I want you to find out what should be the total pressure so that 80% of water vapor condenses out as liquid water. Okay, Aniruddha, can you solve? And can you tell us the solution?
Yes, I'll try, sir. Yes, sir.
Yeah. So is the problem clear to everybody? Now we are increasing the total pressure. The pressure at which first drop of water appears, we call it as dew point, but now it is dew point pressure or pressure dew point. This was our temperature dew point. This was our temperature dew point. Now this is pressure dew point. Okay, Arya, are you there?
Yes, sir.
So I think we are nearing our time. So all of you can continue doing this problem. You have another lecture at 10:40, so we need to stop just now. Aniruddha, can you continue? Can you continue doing, and we will see in your next class. See the solution in your next class. In our next class.
Sure, sir. Yes, sir.
Okay, and Arya. So next Tuesday, I won't be taking the morning lecture, but I will try to take lecture at some other time in the afternoon or evening. But we will schedule that perhaps on perhaps next week. So next week, both Tuesdays and Thursdays morning lectures I will not take, but I will reschedule them on the same day some other time, perhaps in the evening 6 to 8 or something like that. Uh, uh, but then today afternoon, can we have an extra class so that we complete these kinds of problems, and if there are any difficulties we can answer those. So today 2 o'clock shall we meet?
So we have a lab at 4. I guess students have to do the second experiment also. So is it okay if not today?
Okay,
I can place another lecture on Tuesday or Thursday if possible.
yeah, Thursday then you try to fix another class. But today at least 1 hour is possible, because then at least we will do the solution of this particular problem, so that it is
Okay, sir. So 1:30 to 2:30 would do.
so let's meet at 1:30. Okay, so let's do
Okay,
that.
sir.
Let's meet at 1:30. So we use the same link. Aniruddha, will you be able to tell the solution by that time?
Yes, I'll try the problem. So yes.
Yeah. Okay, so let's stop the recording now. So we meet at 1:30 so that we